Okay, so in the last video we were talking about the binomial distribution, and here we are making the connection with the Bernoulli random variable. Right, so if the yi's are Bernoulli, so either 0 or 1, then the binomial, which is the number of successes in Bernoulli trials, is simply the sum of these n Bernoulli random variables. Okay, and here in the table below you have an example. So it's the same we just saw before. We tossed 4 coins, so the outcome of each is going to be our binomial random variables, right? So this is the sample space, all possibilities, right? All combinations we can make, and then the last column is the binomial, right? So the sum of all these columns. So here you can see clearly the relationship between the two. Okay? Alright. So, since we had a sum, then we can use this normal approximation, right? Because x is the sum of other random variables, and that's where this central limit theorem comes in. Okay? So, the normal approximation is due to the central limit theorem. And that's because there's a sum involved, as we just saw, right? So we're going to see how to apply that. But basically the idea is the same, always. When you do a normal approximation, you know the normal has 2 parameters. First is the mean meal of the random variable, x in this case, and the second is the variance. So for the case of the binomial, we know formulas for each. So the mean is n times p, and the variance is np times q. And q is 1 minus p. Right? So that's it. That's the whole normal approximation thing. And we're going to see how accurate that is for typical parameter values. Right? The other corollary, let's say, is that the sum of 2 binomials with the same probability of success is going to be also binomially distributed. Right? So if x1 is binomial with n1 trials and p, and x2 is with n2 trials, then the sum of 2 would be a binomial with the sum of the number of trials. Okay, now that's intuitive. We don't need any math to show it. Just think about the experiment of each x1 and x2, like tossing a coin. Right? So you toss it a coin n1 times, and then x1 is the number of heads. Same thing for x2. You could keep flipping the same coin n2 times because it's the same probability, right? So the sum of the 2 is just keep flipping the coin, and then the number of successes would be just the sum of the 2. So make sure you get that intuition. And again, there's no formulas to prove that, it's just the experiment, right? So think about this experiment, and then this experiment. You'll see that the latter correspond to the sum of the 2. Right. And now this figure will show you how accurate the normal approximation is. So we have p in the first column, and then n in each row. Okay, so you can see the patterns. So usually around this one is good, all these are good, right? Very nice approximations. This is pretty good too if you think about it. Now all the others are iffy. This is okay, this is good, right? So you kind of get an idea of where this approximation works, okay, right? And there's a rule of thumb is that NP has to be more than 5 or so. But you see that even though we don't have this condition here, some cases in this table are pretty good. Alright, so just to get a quick idea of when to use this guy, this approximation. Okay, so sometimes this normal approximation is not very accurate when n times p is very small. Okay, and sometimes this continuity correction that we're going to see now helps improve the approximation. Okay, so let's recap. The normal approximation, right, without continuity correction, just says that, so if x is binomial, then we can say that x is also approximately normally distributed with the first parameter mu equals to n times p, because that's the expected value of the binomial distribution, and a variance of np times 1 minus p, right? Okay, so in that case, one can use equation 413 right here without the continuity equation. And here we're calculating the probability of x being between these two numbers. All right, so let's do a little graph showing what's going on. So this is x, your binomial random variable, which has, discrete numbers or probabilities, right? Okay, let's do these three. 0, 1, 2, 3, for example. And I could keep going, and that should be a 3. All right. So that's your binomial probabilities, and then just as in the figures above, actually, right? And then we would have a normal approximation, and that's the PDF of a normal random variable, right? Mu comma sigma squared. But again, mu is NP, right? And sigma squared is NPQ, because we're doing the approximation to the binomial. Very good. Okay. So let's think about the probability that we've been asked. So let's say A is 1 and B is 3, okay? 1 and 3, just to illustrate. So the exact probability would be, right, is this probability plus this, obviously, right? The height of those 3 bars, not the exact one. Okay, so for the continuity correction, what we imagine is that each integer number has a bound around it of length 1. So from 2.5 to 3.5, that's going to be actually the bar corresponding to outcome number 3. Okay, so it is this area below the PDF, sorry, that's going to be the area of P equals 3. Alright, so that's the idea, is that we have this band of length 1 surrounding each integer number. And if we do the integral along that range, the idea is that we're going to get a better approximation than if we just evaluate the CDF at this point, which is what we did in this chart, right? Right, when you're comparing, I don't know, this exact value with this approximation, that's what we're doing, right? Okay, but here, we're saying that instead of just using the point from the PDF, use this integral, okay? Right. Now, let's do the same for 1. So 1 really lives between 0.5 and 1.5. And the same thing, so the best approximation for x equals 1 would be that area right there. Okay, and finally, for the probability of an interval, right? So in this case, both B and A are included. Right. So let me try to show the exact area. Well, yeah, we showed at the beginning, right? So this is the height of these 3 guys right here. All right, but in our approximation framework, right, the number 2 also should be approximated by this area right there. So at the end, what you end up with is the sum of all those areas, and you see it goes from 0.5 to 3.5. Okay, so going back to the way we calculate probabilities in general for continuous distributions, right, is the probability of the larger end of the interval, so b plus 0.5 in this case, minus the lower end of the interval, so 0.5 in this case, right, 1 minus 0.5. So there you have it. That's your continuity approximation. Sometimes it works best than the other, sometimes it doesn't, so it's not like a bulletproof. All right, and just to make sure we got things under control, let's say, let me change a little bit this. Let's do a strict inequality, either in A or B, doesn't matter. So let's say it's strictly less than X, okay? So in the exact method with no approximation, right, it would, and A is still 1 and B is 3, okay? We would just have the heights of 2 and 3 only, right, because A is no, we don't want A anymore. Okay, so in this case, you see the formula should not include this area right here. So we shouldn't include this area. So the new area is up to 1.5, right? So this number shouldn't be 0.5 in that case, right? So it should be 1.5. So actually we should do plus 0.5, right? All right, so that's the only difficulty with this method, is trying to figure out sometimes you have minus or pluses depending on whether these are strict or not strict inequalities, right? So finally, if you put a strict inequality here, again, the best way is to draw, right? Draw a figure like this to see what's going on. But all right, so if it's strict inequality in both sides, really you just have the number 2. So the exact would be just this one, and then this guy we shouldn't consider. So here it should be negative, right? If we have that situation. Alright, so it's a bit confusing when to put plus or minuses, but this is the best advice, is draw yourselves a nice figure like that. Alright, so let's do this example. So these are, we have wells on a property, I guess, and we know that 20% are contaminated. Okay, then you take a random sample of 4, and we want to know the probability of having exactly 2, fewer than 2, or at least 2 wells contaminated. Okay, and we're going to do this using the binomial, using the normal approximation without continuity correction, and normal with continuity. Alright, so here goes. For the exact answers, they're pretty straightforward. It's just applying the PMF formulas for the binomial, right? And these are the parameters 4 and 0.2, right? So there's 4 wells, and the probability of 1 being contaminated is 20%. Alright, so all these should be straightforward. This one is the complement of the other, so we can just do this and be done with it, or you can compute the remaining terms. You're going to get the same answer. All right, now with the normal approximation without continuity, so normal approximation, we use our formulas for the mean and variance of a binomial. So 0.8 and 0.64 in this case. All right, so for the probability of a given value, right, without continuity correction, it's just this PDF, right? And that's the equation for the PDF right here of a normal and a variable. And we know the values of mu and sigma right here. So, and we get 0.62, which to be compared with 0.15 here. So not too bad. This one, however, is not very accurate. Look. So yeah, this is 1 minus probably less than 1. So that's the phi function for the normal approximation at 1, right? And we get 0.93, which is not very close to 0.82 there. All right, and the other one is just 1 minus that. Now, with continuity, right, we use our formulas that we just saw. Right, so probably x equal 2 is the band between 2.5 and 1.5, right? And now we get a much better approximation. No, actually it's worse. Right, 0.15 is the exact approximation with continuity for a single point. It's not as good as in part B, right? Okay, but the other one is much better. So same as before, but now we apply the continuity correction, right? Okay. And then you have 1.5 here instead of 1 without the continuity. And it's because of these bands that we put. And now this guy is much closer to the exact solution up here, right? 8.82, 8.81. All right, so there you have it, how to use with and without continuity corrections. Very good. We're going to do this one in class. Please read it. So here's the tornado example once more. Okay, now we're going to talk about the multinomial distribution. It's going to be rather quick though, because it's kind of a straightforward generalization of the binomial random variable. Okay, so think of it as a binomial experiment, but where the underlying Bernoulli experiment has k outcomes and not just 2. That's the Bernoulli. All right, so here we have k possible outcomes in this experiment. And each outcome has its probability pi to occur. All right, and then the random variables are several. Well, the k random variables, one for each outcome, right? And the random variable would be ni, is the number of each outcome that you have. All right, so you perform the experiment, and the experiment is, it's again doing this basic, they're not Bernoulli, let's call it extended Bernoulli trials, right? It's like, yeah, it's like instead of tossing a dice, it's flipping a, sorry, instead of flipping a coin is rolling a dice, actually, right? K would be 6 in that case. All right, yeah, that's a nice intuition there. So, and I again is the, so you roll this dice 10 times, and I would be, and 1 is the number of 1s, and 2 is the number of 2s, etc. Right? So n is the number of each possible outcome. Okay, and then we have the joint, that would be a PMF. We say distribution, but we mean PMF here. Right, so let me expand this notation. This is the probability that n1 equals little n1, like that, etc. Okay. So it's a PMF. It's the probability of any particular outcome of this experiment. And again, think of rolling a dice 100 times. So what's the probability that you obtain 20 number 1s, 17 number 2s, etc.? Okay. Now, something that we should have said before is that the sum of all these probabilities should be 1, right? And this is your PMF, okay? Now, the logic is the same as the binomial. So first of all, you have the product right? This is the product of all the PI's to the NI's, because that's the probability of obtaining the event that you're looking for, right? So you're looking for 20 number ones. That's going to be 1/6 to the 20 times 117 number twos. It's going to be 1/6 in the same, because it's a fair dice, let's say, to the 17th, etc., like that. And then what's before the product, you see that's the same equation for the number of combinations you can make among a total of n objects, and they're identical, right? So n1 are of type 1, n2 type 2, etc. So that's the number of arrangements that you can make in this sequence, the same way as in the binomial, right? So yeah, it should be a straightforward generalization of the binomial. Okay, and then these are the things we need to know about the multinomial. It's expected value invariance, so the same as the binomial if you think about it, right? And it's because this fact that we're not going to prove, but is that the marginal distributions are all binomial. Okay, so we don't need a fancy proof. It's just, again, by looking at the experiment. Right, so going back to the dice, rolling a dice 100 times. If you only ask the probability of obtaining 20 number ones, all right? So that experiment is the same as just rolling the dice 100 times, calling a number 1 a success and everything else a failure. So that's why it's a binomial distribution, right? Because if you do that, then n1 is binomially distributed, right? So the outcome 1 is the success, but all the rest is the failure. So that's when you kind of take the marginal, because you don't care if it's a 2 or a 3 or 4. It's not 1, that's all you care. So it becomes a binomial. All right, so all the NI's are binomial with parameter n and the probability of success corresponding to that I. All right, so what's new here is that we have a covariance term between any two outcomes, which is negative, right? And it should be intuitive, right? Because if you, again, roll the dice 100 times, if you know that you obtained, let's say, 99 number ones, just let's say that, then you know that the others are much more likely to not be the outcome, right? So in a sense, it's kind of the sum is fixed, 100. So the more you have from one type, the less you have from the other. So that's why it's going to be negative like that. All right, so I think I just have one example of this type. All right, so just going to use it very sparsely. All right, so let's read this. Take a minute. Okay, so here we have, I guess, the delivery of supply kits, and then 60% are recent, 30% are moderately aged, 8% are aged, and 2% are unusable. All right, so we have these 4 categories. And then we choose 16 kits, so that would be N. All right, and then N1 and 2 and 3 and 4 are the number of the type of these supplies, okay? All right, so part A, find the probability exactly one of the 16 reactions will not be performed due to unusable. All right, so the question, it's only regarding N4, the number of unusable kits, unusable material. All right, since the question only involves one, it's the marginal, And the marginal of a multinomial, we know it's binomial. So n is 15, probability of success for 4 is 2%, right? Right here. So we know how to do these already. Alright, part B. Find probability that 10 chemical reactions will be performed with recent material, 4 with moderate, and 2 with aged. So they give you 3, right? 10, 4, and 2. And since the sum has to be 16, it turns out that n4 has to be 4. I mean 0. Right? So that's the probability that we've been asked. So this is a PMF, and we know the formula right here. So that's it. And finally, about the correlation, so we expect the correlation to be negative, right? So the more you have from one type, the less you will have from the others. And then we can calculate the covariance explicitly with the formula. It's negative 2.88 in this case. All right, pretty straightforward. That's all we're going to say about the multinomial random variable. All right, let's keep going through this family of Bernoulli random variables. Next one is the geometric, a very useful one. And so it's also in the context of Bernoulli experiments, so flipping a coin. Here we're asking the question, how many trials or how many times do you have to flip that coin in order to observe the first head? Okay, so or in general, how many Bernoulli trials until the first success occurs? All right, it's a very common random variable, right? How many buses until my bus comes at the bus stop, right? How many, how many minutes should I wait for something? Each minute would be a trial there. It's a very common distribution. Okay, so that's our notation. The word geo means geometric, and it only has one parameter, p, the same parameter, p of success. All right, let's start with the PMF right here. It's q, remember q is 1 minus p to the x minus 1 times p. Now the best way to see why this PMF is true is with this trial number line right here. So the probability, the PMF, right, acts for the probability that x equals little x. So that means what is the probability that the first success happens on trial number x, as in here. Okay? So if this is going to happen, you see very clearly that the first x minus 1 trials have to be failures. And then the very last one is a success. Okay, and the probability of this sequence, right, so you have x minus 1 failures, the probability of that is q to the x minus 1, and finally the last one has to be a success, then we multiply by p. And why we do that is, again, it's the multiplication rule in chapter 1, right, and it's the event of the intersection of all these trials, right, and the intersection of all these events is, so the events are the first x minus 1 are a failure, and the last one is a success. Since they're independent, we can go ahead and multiply those probabilities. All right. Again, we can apply the formulas for mean and variance. We would obtain these two. So the expected value one is important. We're going to talk about in the next slide. The variance q over p squared, and then we have a shortcut formula for the CDF, and we're going to see where it comes from in a minute. All right, so this is one of the exceptions with the discrete random variables, where the CDF is actually analytical and is easy to evaluate. Okay. All right, and finally here you see in this graph the typical shape of these geometrics. Now, in general, you shouldn't do this, and by this I mean connecting the points, but I just want to show you the shape of this distribution. So it's like an exponential decay. And we'll see that the exponential random variable is closely related to. Okay, so these are geometric series, so at each time you multiply by a constant, the same constant. So they're decreasing functions, monotonically decreasing despite my bed. There you go. All right, so continuous decreasing, going to 0, and they start at the maximum value there, at x equals 1. Oh yeah, I should have said that here x is defined to be greater than or equal to 1. So actually 0 shouldn't be here. Right, because at least you have to toss the coin once. Right? Okay. Now, the expected value, we said that it was equal to 1 over p, right? From the slide before. That's the expected value of a geometric random variable. Now, it turns out that we call 1 over p, actually we call it the return period, capital T. And it's because of this reason, that for the geometric, the expected value of x is 1 over p. Now, the expected value is kind of the average time between these events, right? Because remember, the definition of x is the number of trials until the first success, until the first event, let's say. So the mean time between events is the expected value of x. Turns out to be 1 over p, okay? Which means, and this is, right, so this expected value between events, we call it the return period. Okay, now the significance of this is that it's, typically people refer to these events with the return period, like the 200-year earthquake, right? Or 200 wave height, or anything like that. Right? The 100-year, whatever, really, right? Economic depression or anything. So it's like this idea of having the average time between these events gives you the probability. Okay? So many of these examples, they'll give you the return period. They won't even say that it's geometric, but one has to assume that it is. Okay. So let's see the connection between the geometric and the binomial, which is actually how we obtain the expression for the CDF of a geometric. Okay, so we have our number line right here to start with. And again, that's the definition of x for the geometric, right? So x is a trial with the first success, right? So that's your x random variable. Now let's define y to be in the binomial NP. Okay, binomial, number of successes and these n trials. Okay, and we have the same probability p. Okay, and then from the figure, okay, we have this. Look. So first, probably x is greater than n. This represents, in English, this means, what is the probability that the first success comes after trial n? Okay? Kind of what we have here in this figure. So we have the trials, and again, we should start at 1, from 1 to n. Now, here between n and x, you could have several. Don't think that n and x are one next to the other. Like that. Alright, so what it means, if the first success happens after trial n, it means that in the first n trials, there were no success. Right? Just by It's kind of silly to say it, but it's important. So it's the same event, but expressed in terms of two different random variables. And that's what connects them. Okay? So again, in terms of x, as the first trial happens after n, in terms of the binomial, is that in the first n trials, there were 0 successes. So probably y equals 0. We know how to evaluate that. That's the PMF of the binomial, which is only, so simplifies to q to the n. Right? And that's why we have now this important equation. For the CDF, right, we just take 1 minus, and you get the CDF of a geometric random variable. You know, instead of doing the typical, you know, summation, it would be, you know, use I equals 1 to x, I guess, of the PMF, which would be q I minus 1 times p, right? So this one is hard to work with because you have a summation, but this one is easy. It's just, right? But they will give you the same answer. All right. Now, the geometric distribution is one of two distributions that have this important property, which is called memoryless. Memoryless property. Which means that when you're evaluating conditional probabilities on the number of events occurred so far, or the number of trials occurred so far, doesn't affect the probability of your event. So, for example, here we're saying, what is the probability that the first event happens after trial I plus j? Alright, so I is here. Let's call it the present. So you're flipping this coin. I is 10, so you flipped it 10 times, and you still no heads. And you ask the question, what is the probability that I have to flip this coin j more times in order to get this guy? In order to get a head. Okay, so that's the conditional probability. Now, it turns out that it is equal to simply the probability that x is greater than j, so greater than the remaining number of trials. Which means that it's kind of the, it forgets what has been going on until the present, right? Because this probability does not depend on I. The I cancels out somewhere. We're going to see where. So there's 2 points. Here, one is independent of I, right? Which means that it forgets right? So the present doesn't matter. How many times you have flipped the coin doesn't matter. The number of times you have to keep flipping is always going to be the same, so to speak. Which makes sense, right? Make sure it makes sense to you. And the other important property here is that it's still geometric. Geometric. With parameter p, actually. Right? Because it's the same random variable x, which is geometric, greater than j in this case. Okay, so all that matters for the geometric is the number of additional trials j, which also has the geometric distribution, right? So that's why we call it memoryless. Again, first, it doesn't depend on I. So the present doesn't matter. How many times you flip that coin before doesn't matter. And it's still a geometric random variable with the same parameter, right? So it's like nothing happens really. Now, in the case of flipping coins, it's intuitive that it should be memoryless, right? Because all these experiments are independent. So it doesn't matter how many times you've won, the expected number of trials to win again, it's independent of the past, right? Because it's the same coin that you're flipping. Okay, so we're going to revisit memoryless property when we talk about the exponential, but in the case of the exponential, it's not easy to get the intuition of memoryless, but here for the geometric it is, and it's because, again, we have these Bernoulli trials that are independent. Very good. And here's the proof. Please take a look at it. It's just definition of conditional probability. The intersection of these two and the numerator is just this one. And then when we replace by what they are, using the CDF formula, we just obtain q to the j, right? Because the I cancels out here. So that's right, and that's the CDF, or this 1 minus the CDF, right, of a geometric with parameter p. That's the big deal, right? And this happens only, again, with the geometric and the exponential situation. Very good. All right, I ran out of time, so please take a look of these examples and we'll discuss them during class. All right, see you guys.